let's start with the last part for the morning session. So multi-threading. So nowadays we are in the so-called multi-core age for CPU. If you look at this figure, which shows you the development of CPU processor from the 1970s until now, you will see that the number of transistors, as you see this line, is continuous increasing, but the performance for single thread is not really increasing linearly as the number of the transistors. It's still increasing, but not really dramatically. And if you look at the frequencies, you will see that, let's say, in the last 20 years, from about 2005, there's no change for the CPU frequency. And power consumption is also roughly flat because, if the power consumption continue to increase, this computer will be a real heater that is not really usable, so that the power consumption must be relatively flat. But one big change you will see is the number of the logical cores. So basically, from roughly 2005, roughly 20 years ago, this is a scale of the power of 10. So previously, 10 to the power of 0 CPU cores per socket, so only one core. And now, as you can see, 100 cores roughly, it's very common. So that is why we are in the so-called multi-core age of CPU, and we need to take advantage of this multi-core. And that is why multi-threaded programming is very efficient and the key technology to do parallelization. So in this part, I'm going to give you a very high level and quick overview. If you want to dive into more details, we can talk about maybe later or maybe in some other occasions. But in this part, it's only a very high level overview. So if you look at one compute node from Noctua 2, there are two CPU sockets. This is a figure, let's say roughly demonstration. It's Zen 3 microarchitecture with 64 cores per socket. And in total, you will have already more than 100 CPU cores per compute node. And in order to utilize all those computational powers, 128 CPU cores, you can do multi-threading based on the so-called compiler directives using OpenMP, because this is very convenient and very efficient to utilize multi-threading. And as I mentioned, we are going to use OpenMP, a very short, brief story about OpenMP. OpenMP is a portable solution for shared memory programming, so basically for multi-threading. And you can use it for C, C++, Fortran, and there are multiple or many compilers available supporting OpenMP. So you can use Intel compiler, you can use GNU compiler, you can use I don't know, Clone, this LLVM supported compiler, NVIDIA compiler also supported. And you can easily put a serial code into parallel code by using OpenMP. As you can see, there is a, let's say, development for OpenMP from version 3 to version 4, version 5, and so on. So more and more functionalities are added into OpenMP. Now, because you said you would like to program GPU, you can use OpenMP to program GPU, of course. Yeah, we have a section in HBC for this. yeah, you can also use OpenMP to program GPU. But this topic is not covered here because here we only have a limited time. So first, I would like to give you a very high-level overview about how OpenMP works, yeah, without talking about details about OpenMP. So OpenMP programming model is very simple. It's the so-called fork-join parallelism. So in the beginning, the start of your application, you have the so-called master thread, right? Only one thread, nothing fantastic. But then you can fork this master thread to spawn a team, a group of threads to form the so-called thread region. You know, for CPU, this can be, I don't know, 1, 2, 3. Or for GPU, you can have millions. Yeah. So, but anyway, the basic principle is the same. And then you need to do some, synchronization among those threads. And then there is the point to synchronize. But here you have the so-called parallel region, right? Because in this region you have, I don't know, 100 CPU threads or 1 million GPU threads. It's parallelized, it's parallel region. And then in the next phase, a next calculation in your program, you may want to start, I don't know, different numbers of threads, maybe more or maybe less, I don't know. And then you start another parallel region, and then you synchronize again. And then you start another parallel region, and then you synchronize again. And then the execution of your code finish. So basically, this is a high level of overview about how OpenMP works. Yeah, so in different parallel regions, you have the freedom to create whatever numbers of threads. Yeah, it's based on the character of your application. So in this course, I'm going to introduce you those OpenMP compiler directives by using C, C++, and Fortran as example. Yeah, we still have active Fortran developers here, so that Fortran is also important. So for C++, you can use this pragma OpenMP, as an indication. Okay, we will use OpenMP directives, and then followed by construct, like sentences, and then clause, like sentences to describe the OpenMP. Fortran, the same construct and the same clauses. The only difference is the beginning part. This C $OMP, it's the Fortran style. And if you are using C, you need to include the C header file. If you are using Fortran, you need to include the so-called Fortran module file, OpenMP library, the Fortran module file. And yes, as I mentioned, multiple compilers support OpenMP. For Intel compiler, you can use -fi OpenMP or Q OpenMP, GNU compiler -f OpenMP. For NVIDIA compiler, you can also use this with -mp, but I'm not putting here because, yeah, for this course, we only use Intel compiler, GNU compiler. So for the OpenMP construct, it is like a blocked structure. Like you can see, a structure that has a block. Let's look at the C code. No need to fully understand the C code, but you can see it's a block. Yeah. Inside this block, you have those OpenMP or whatever statements, but this OpenMP parallel form this block. And inside this block, let's say only a few is allowed to jump, jump out of this block. So basically exit or stop. So basically, if you want to stop the entire application, you are able to jump out of this block. Otherwise, it's not possible because you are in a parallel region. And inside this block, if you run this application, TID is the thread ID, NTD is the number of the threads. So you can use OpenMP function calls and then to get the number of the threads in this block region and also the thread ID in this region. And here you see the output. On the right side, you see the output. Normally, for most of people, they think, okay, we will have a regular output. Regular means, yeah, thread 1, thread 0, yeah, because we are using the C version starting from 0. Thread 0 of 8 threads, thread 1, thread 2, thread 3, and so on. No. Inside this parallel region, it's somehow out of order executed. There's no definite order. Yeah. So that is why here you see thread 0 first, and then thread 6 first, and so on. If you run this program again, you may see, I don't know, thread 2 first, thread 6 somewhere. Yeah. So this is multi-threading. Inside of this is out of order. But you need to make sure that even though those threads are executed independently, you need to make sure in the end of the day, your program gives you correct result. So let's talk about the so-called OpenMP memories. So basically, there are two types, from high level, two types of memories in OpenMP. As you can see here in this graph, we have 4 threads, and the first type of the memory is the so-called private memory, private to the thread, only available for one thread. The other threads have no access to those. And another part of the memory is the so-called shared memory, which is available for everyone, like a shared resources. So those concepts are very important, because otherwise you may have some unexpected result. Like previously, we have this thread ID, TID, and number of the threads, right? We have those two variables outside of the parallel region, yeah? Outside of the parallel region, and we simply give it OpenMP parallel. And then inside this parallel region, those variables outside of the parallel region will be by default, let's say, shared among all the threads. And then if we want to print out the thread ID and number of the threads, you will see that, for example, the thread ID 6 is printed multiple times, and the thread ID 1 is printed 2 times, and no thread 3 or no thread 4 or so. Why? It's not because thread 3 or thread 4 does not exist. It's because those thread IDs, they are in the shared memory. The other thread override the thread ID of, for example, thread 2 or thread 4. That is why they are not printed out. So that in this case, you have some wrong, let's say, wrong output of your application. In order to fix the problem, you need to put the variables in the correct memory type. And for the correct memory type, there are many, for example, shared or private, first private, last private, and default. Yeah, because of the time reasons, I'm not going to talk about all those details. The two most important ones are shared, like shared among all those threads, and private, which is only accessible for this thread. So, thread ID is a private variable. In this case, you must specify, okay, thread ID is private. Otherwise, the value of thread ID will be overwritten by some other thread, and the output was wrong, like you have seen this. And our recommendation is to use default none. So basically, specify no default attribute for any variable, so that this forces the programmer to specify everything clearly. This may make the program more clear to understand. So as an example, for C, let's forget about the Fortran part, but the Fortran part is the same for OpenMP. We just specify, okay, default none. And then a number of the threads is shared, because anyway, in the entire parallel region, the number of the threads is the same, right? You start 8 threads, it's 8. You start 100, it's 100. There's nothing to worry about. And then thread ID, the TID, this must be private. This must be private. Otherwise, you know, the thread ID from thread 1 may be overwritten by thread 2 or thread 6, I don't know, and then the result is will be wrong. So this is a hello for OpenMP. And then let's talk about the so-called work sharing construct. So what's the meaning of work sharing? So basically, the principle for parallelization is very simple, right? You have a large amount of workload, and then you need to share this workload among different threads. That is why here we have the so-called work sharing construct. And then by sharing this work, you can achieve parallelization. So the most commonly used work sharing construct is the for loop or do loop in C or Fortran. But also there are so-called sections and also single construct. But I'm not going to talk about sections and single in this course. Let's just focus on the so-called for loop or do loop. So to understand this, it's very simple. You have one thread, and then you have a parallel region. And then inside this parallel region, you have multiple threads, let's say 4 threads. And then 4 threads working on this for loop or do loop together by sharing the work. So to start multiple thread, we have talked about this by using OpenMP parallel. As you can see, start the multiple threads, and then you can partition this work to share the work among those threads. To do that, for the for loop, very simple, just put it OMP4. And then that's it, just put it OMP4. And then for this simple example, to add 2 vectors and then store the result in one vector, the effect of OMP4 can be visualized here from the right part. Yeah, you have 3 vectors, and then the work will be divided into 4 threads, and each thread works on their own part, and then finally to have a barrier to synchronize and then to continue. Yeah, this is conceptually very simple. And for the work sharing, as you can see, the traditional form is relatively long, and then OpenMP has this combined form, which means you can combine the spawn of the threads and work sharing together, so that you needn't to write very lengthy OpenMP directives. Here, as you can see, now it's very concise. OpenMP parallel for, just do it in parallel, do it for the for loop, and then default none means the default variable is not specified, but you need to specify it clearly. Vector A, B, C, those are shared, and the variable I is private. Yeah, and then you achieved parallelization for this code. And another important aspect for multi-threading is how to schedule those threads. For OpenMP, there are multiple options. So basically, the most commonly used is the static option. So this means you have roughly a predetermined size of work for each thread, and then they will be scheduled, statically, like predefined. And dynamic means there's no predefined workload for each thread, And then the runtime takes care of how to schedule those threads. There are also other options. I'm not going to dive into details because limited time. So a question from your side may be when to use static scheduling, when to use dynamic scheduling, right? Because why they are useful. So basically, a rule of thumb is if the workload for each thread is roughly equal, yeah, not identical, roughly equal, and then you can use static because this static scheduling has been determined early, and there's very less overhead. You know, the threads just run the calculation. But if the workload is unclear, for example, the workload for testing if a number is a prime number, this is unclear, this is unpredictable. And in this case, it's better to use dynamic scheduling. And then the scheduler is able to fill the threads if they are free. Yeah. And maybe in your code, you may have, let's say, some very short loops. For example, a loop of only 8 iterations, right? Think about Noctua 2. One compute node has 128 CPU cores, but here you only have 8 loops. And if you do parallelization for a loop, a very short loop, this is not really useful, right? Because the loop is too short. So how to do that? You need to make multiple short loops to become a larger loop, right? If you have a short loop, this short loop cannot saturate 100 CPU cores, maybe in the future several hundred CPU cores. And then a solution is to combine multiple loops so that you are able to distribute the work to all the CPU cores. And one way is to do this manually, you know, to change your source code. This is possible, but this is actually not recommended because you change the code structure, sometimes makes the code not really readable. For example, yeah, what's the meaning of k divided by 205 and then calculate the remainder of 8? What's the meaning of this? This looks not really immediately clear. So manually it's doable, but not recommended. So to solve this problem, there is a very short but useful clause from OpenMP, the so-called class. You know, just use this one, and then those two short loops, this loop of 8, loop of 200, will be collapsed into one larger loop, which is about 2000. And a loop of 2000 is much better than a loop of 8 for 100 CPU cores, right? Because you have more enough workload. So this is a good solution. And then I would like to talk about a very important topic for multi-threading, the so-called race condition. Race condition, like you have 100 threads, and those threads, they are running like a race, you know, for doing sport. And then someone runs faster than the others, and then you may have some wrong result if there's something wrong. Here, this code calculates the dot product of two vectors, A and B, and then return the dot product, the sum. And then the loop is very simple, right? Just a for loop and then calculate the sum. The loop is very simple. And a naive implementation would be just a copy paste. You know, previously we talked about parallel for default shared private blah blah blah, put it there and then just let it run. But unfortunately, it does not work. It does not work. Why? Because if you put the sum into the private section, like if the sum is in the private section, this private variable is only available in the parallel region. But you need the result outside of the parallel region, for the synchronize, like this fork and join. You need to join in the end of the day, so you cannot put it into private. But you put the sum, the result sum into the shared part, you will have the race condition, because one thread may changing the sum, and the other thread may also changing or reading the thread, reading the sum. If you have, I don't know, 100 threads, this is like a chaos. So in the end of the day, the value of sum is unpredictable. This is wrong. This is wrong. So in order to solve this problem, you can use the critical directive from OpenMP to put this part, the calculation of the sum, into the critical region. So this means, okay, this is a critical region, and only one thread is allowed to modify or to read this sum. The other thread, they must wait, because otherwise, this is like chaos. So we need the correct result for sum, and then we have to put it into the critical region. And the disadvantage is quite a lot. The first one is, so basically, it creates a very large overhead for many different threads, because inside this critical region, only one thread can work, or only one thread is allowed to work. The other threads must wait. This is not wanted, because the other threads are waiting and doing nothing for the calculation. And also, this makes the calculation serialized, because once upon a time, only one thread is working. And then another thread comes in, work, and the other thread must wait. This is not wanted. Although this gives you the correct result, but there's no parallelization. So in order to solve this problem, we need to, let's say, minimize the critical region. Not always have this critical region. To do this, we need to create a private local variable for each thread, like this s local, some local thread, and then we put it into the for loop, and then just let this for loop to do the summation, to do the sum for the local sum. And then, because each thread has its own local sum, there's no race condition, there's no dependencies, because they just work on their own thread. And only in the very last step, we summarize the local thread, the local sum, to the global sum. But for the summarize the local sum to the global sum, this is very limited number of local sum. Only, I don't know, 4 or 100. So this can be done very efficiently. But anyway, there are still opportunities to further optimize. I talk about this very quickly. A further opportunity is to use no wait. For the local sum, each thread needn't to wait for each other, so that you can do no wait. So just let each thread go without synchronization in the end of this for loop. I talked a lot for how to do the critical region, but actually the best solution only comes right now. Yeah, the best solution comes very late. You can use the reduction clause to do the summation for the add operation. By using this single reduction clause, you can get rid of all those data races or critical regions, whatever we mentioned previously. And for reduction, you only need to indicate the operator, which is plus, and the variable, which is sum. This is the most efficient way to do the calculation to get rid of the data race condition. And for using reduction, this dives into the content of reduction inside a parallel region. I would like to skip this because this is a little bit deep. And but anyway, if you have this reduction of many elements into one element, for example, like add or minus or multiply or logical or operations, you can use reduction clause. This is available for C++ and also for Fortran. And if the reduction operation is not available, unfortunately, you have to implement it by yourself. Yeah, there's no reduction for very complicated operations. Yeah, you have to implement it by yourself. And the very last part I would like to say is about SIMD vectorization. By using OpenMP, you can use SIMD. SIMD means a single instruction for multiple data, so that with one single instruction, you are able to do calculation on multiple data. But I would like to talk about more about SIMD in the afternoon part. Here is just a preview to show you. Yeah, if you are using scalar instructions to add 4 numbers, you need 4 instructions, right? Because you want to add 4 numbers. But with SIMD, this is not multi-threading, this is SIMD. This is done by using one single instruction, like this one single plus. You are able to add 4 numbers, just one single instruction. This gives you actually 4 times speed up, even with only one single thread. Okay, for using OpenMP, not only those directives I mentioned before, you can also use the so-called OpenMP API functions, right? There are multiple important API functions you can use. For example, get the time, runtime for one thread, get to set the number of the thread. For example, in the parallel region, get the total number of the threads, get the thread ID, and so on and so forth. There are multiple interesting OpenMP APIs you can use. And also, you can use environment variables, to control the runtime behavior of your OpenMP code. Yeah, this is more gives the freedom to the user of your application, so that the user can change some settings to make your application run more efficiently on the HPC cluster system. We are slightly over time, but not really seriously. So this is the end of the very high-level OpenMP part, and also the end of the morning session. I'm not sure. Do you have any questions about parallel programming or OpenMP or whatever, so that we can talk shortly? Yes?
If there's no other question, can you go more into detail about the no wait option? Because I was wondering, like, why would they wait otherwise?
Yes, because by the OpenMP standard, there is always a synchronization in the end of the for loop. As you can see, this implicit barrier. This is the third sentence. Threads must wait at the end of the parallel region. Why? Because of the so-called fork join parallelism model. So in the beginning, you have this fork, and then in the end, you have this join, and then fork and join. So this is that's the OpenMP fundamental model. But for this one, for this calculation, this S local is local for each thread. So there's no dependency for S local for thread 1 and S local for thread 2. There's no dependency. If there's no dependency, you needn't to wait, right? Just let it go. There's no need to wait. Just go. And then you have this critical region. Yeah, in critical region, of course, the threads must wait because otherwise you have this race condition. So for the OpenMP multi-threading part, the first task is to write a Hello World application, and then to print out the thread ID and number of threads and so on in this application, and also to use the OpenMP function, OMP set number of threads, and also OpenMP environment variables to set different number of the threads. So here I have an example code. So you can also copy this example code from this directory. Yeah, this very simple example code, like what I did during the talk this morning before lunch. We just set the thread ID, number of threads, and then print. Yeah, this and to run this job, you need to write this job script, and then this is optional. Yeah, but of course you can set this number of the threads. Let's give it 18, and then to compile and run. So it's very simple. Yeah, you can ignore those warning messages, and then you will see those output like thread ID, number of threads, and so on. So basically, one key observation is the thread ID is not sorted, right? You see 2 first and 0, you know. If you run this code multiple times, it will changes anyway. There's no definite order for this. Yeah, to convince you, I see you are still doubt. So let's run this 3 times. Yeah, the job is very fast. As you can see, there's no definite order for the ID. As you can see, it's like a real math. So, but anyway, this is the basics of basic principles for this exercises. And yes, to make this more approachable for you, so that you can also take a look at the details. Here, I think you can see this solution branch. You can go to the solution branch and then click the solutions. Let me make it larger. And then if you click the solution, you will find the source code there. And then I think this is useful. Even after this course, you can look at it in more details by yourself. Yeah. And for the second exercise is basically if you click the solution, you will see the source code there. So basically here we are using OpenMP get time, while time, to have start, and then OpenMP get time to have a stop, and then stop minus start. You can measure the runtime, and then you can measure the performance. But the key for the performance measurement is about the so-called scheduling. Here, different schedule. If you are using static schedule, you will have good performance. But if you are using dynamic schedule, the bandwidth is very low because the operating system or the CPU, they are busy with scheduling the threads, not running calculation. This is not what we want. Yeah, so you can go to the source code, to tune to tune this scheduling from static to dynamic. For example, dynamic, and then run this job script. You will see the bandwidth is extremely low. Yeah, because the operating system is busy with scheduling. Yeah, so this is not what we want. Anyway, the solutions are there. You can take a look. So I think this is helpful. Even after this event, you can also continue the learning. I'm not sure. Do you have any further questions, or now it's clear for you? And also for the online participants, is everything clear for you, or you still have some questions? Seems there's no question. Yes?
Explain a little bit more how the calculation of the memory bandwidth is done. Like, you got the time, how long the code needed to execute.
Okay, so the one question here is how the memory bandwidth is calculated. So basically, here you have let's say a start point, and then this OpenMP parallel blah 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 start the so-called parallel region, right? And inside this parallel region, you have, I don't know, 128 threads. And for this memory bandwidth, you can see here you have a memory read of vector x. Here you have another memory read of vector y. And here you write something to y. So here you have a memory write to y. So in total, you have 3 memory accesses, right? So that is why here you see this is 3. And you have in total n elements. You can see this is a big N, which is a large number, 2 to the power of 26. So this is N, so you time N. And here we want to have a gigabyte per second. So for gigabyte per second, you need to multiply this prefactor, which is to the power of -9, right? And because here we are using byte. So if we want to have a megabyte, it's 10 to the -6. If we want to have gigabyte, 10 to the -9. And then for each element, it's a floating point number. A floating point number, the size is the size of this floating point number, and then divided by the timer. And then you will see the memory bandwidth for this is some value. Yeah, but this small program has an serious performance issue. I'm not sure. Anyone noticed? I think Alex noticed the performance issue. Alex knows the performance issue. Anyone noticed the performance issue as a bonus to this exercise? There is a performance issue about this code. Any? Yes, please. Yeah.
This must be the initialization.
Sorry?
The initialization.
Yes. Great. Yeah, you can have a earlier fire event for today. You can leave early. You can forget about the very last course. Yeah, you are allowed to leave. Okay, that's it. Yes, you are right. The initialization has a problem. Okay, I think that's yes.
Sorry, just to reiterate on my question. So it's a given that the performance here depends on the memory and not on the calculation on the CPU.
Yes, exactly. Yes, exactly. Correct. Yes, I think this is a very good point from John. So this calculation depends on the memory. It not bound by CPU. And for detailed analysis, I would like to introduce Alex, because Alex will tell us why this depends on the memory, not on CPU. Yeah, for the next session, Alex will make it very clear.